Welcome dear learners. We are continuing Unit 2 Chemical Bonding and Molecular Structure. In this module we are discussing molecular orbital theory of homoatomic molecules. Contents of this module are homoatomic molecules, formation of molecular orbitals or MOs, energy level diagram of molecular orbitals, MO configuration or molecular orbital configuration, bond order, significance of bond order, and magnetic behavior of molecules. First of all, we are discussing homoatomic molecules. What are homoatomic molecules? Homoatomic molecules are molecules composed of only one type of element. These molecules contain identical atoms bonded together. Diatomic molecules are having two atoms of same element. Some diatomic molecules are shown here: hydrogen H2, oxygen O2, nitrogen N2, chlorine Cl2. All these are good examples for homonuclear or homoatomic molecules which are diatomic in nature. Now, triatomic molecules. These comprised of three atoms of the same element. So, triatomic molecules are homoatomic molecules with three atoms of same element. One simple example is ozone. Polyatomic molecules are also there. Homoatomic molecules may be polyatomic if they have more than three atoms of the same element. Examples are phosphorus, which is notated as P4 because a phosphorus is tetraatomic or simply it is polyatomic. Sulfur is S8, it is octaatomic. So, those with more than three atoms can be considered as polyatomic. So, phosphorus and sulfur are polyatomic molecules. Now, formation of molecular orbitals. It should be noted that molecular orbital formation, their energy, their electronic arrangement, bond order, etc. are core concepts of molecular orbital theory. So, before entering into more details about the bond order and higher level concepts, we have to revise the concept of formation of molecular orbitals. The molecular orbitals are formed by linear combination of atomic orbitals. In the previous module, we just learned about the concept of linear combination. Linear combination is a mathematical combination which may be addition or constructive combination or subtraction or destructive combination of atomic orbital wave functions. Bonding molecular orbitals are formed by in-phase combination of atomic orbitals. The antibonding molecular orbitals are formed by out-of-phase combination of atomic orbitals. This linear combination of atomic orbital wave function can be represented by taking psi A and psi B as component wave functions of atomic orbitals. Bonding molecular orbitals can be represented as psi BMO equal to psi A plus psi B. You should keep the fact that the positive sign represents the constructive combination or addition combination of atomic orbital wave functions. In a similar way, antibonding molecular orbital wave functions are formed by the subtraction combination or destructive combination, which is represented like this: psi ABMO equal to psi A minus psi B. So, we can conclude like this: with respect to linear combination, bonding molecular orbital wave functions are formed by constructive or addition combination of atomic orbital wave functions. At the same time, antibonding molecular orbital wave functions are formed by destructive combination or subtraction combination of atomic orbital wave functions. That all about the case of linear combination of atomic orbital wave functions which lead to the formation of molecular orbital wave functions. Now we are discussing overlapping of atomic orbitals. The two atomic orbitals can overlap to form molecular orbital, and I mentioned already in the previous module that the overlapping gives us a physical picture, whereas linear combination gives us a mathematical picture. Both represents the formation of molecular orbitals. We are now focusing on overlapping of atomic orbitals. Two atomic orbitals can overlap to form two molecular orbitals, out of which one of them lies at a lower energy level than the overlapping atomic orbitals and is called bonding molecular orbital. It is very well clear that the energy of the bonding molecular orbital is less than the participating atomic orbital. At the same time, the second one, the other molecular orbital, lies at a higher energy level than the atomic orbital, and that is called antibonding molecular orbital. That is, we can say like this, the energy of the antibonding molecular orbital is higher than participating atomic orbital. Now, end-to-end overlap leads it to sigma molecular orbitals. Lateral overlap leads it to pi molecular orbitals. Overlap may be of two types, and they are end-to-end overlap as well as lateral overlap, out of which end-to-end or head-on overlap leads to the formation of sigma molecular orbitals, whereas lateral overlap enable the formation of pi molecular orbitals. Now, this is the representation of 1s orbital overlap. Two 1s orbitals overlap together in an end-to-end fashion to produce sigma 1s bonding molecular orbital and the sigma star 1s antibonding molecular orbital. The energy of the sigma star 1s antibonding molecular orbital is higher than atomic orbitals 1s as well as the bonding molecular orbital sigma 1s. Now, the 2s orbitals on one atom can combine with the 2s orbital on another atom to form a sigma bonding molecular orbital, that is sigma 2s, and a sigma star 2s antibonding molecular orbital, just like the sigma 1s and the sigma star 1s orbitals are formed from the 1s atomic orbitals. That means 1s and 1s combined together can lead to sigma 1s and sigma star 1s. 2s and 2s can overlap together to produce sigma 2s and sigma star 2s. Now, the end-to-end overlap between 2pz orbitals of adjacent atoms leads to the formation of sigma 2pz bonding molecular orbital and sigma star 2pz antibonding molecular orbital. This is the pictorial representation of orbital overlapping of two 2pz orbital, that is end-to-end overlap. Here you can see the end-to-end overlap between two 2pz orbital, which enable the formation of sigma 2pz bonding molecular orbital and the sigma star 2pz antibonding molecular orbital. The antibonding molecular orbital sigma star 2pz is higher in energy than participating atomic orbitals as well as bonding molecular orbital sigma 2pz. Now, the lateral overlap or sidewise overlap between 2pz orbitals of the adjacent atoms leads to the formation of pi 2px bonding molecular orbital and a pi star 2px antibonding molecular orbital. I already mentioned the fact that lateral overlap or sidewise overlap of atomic orbital leads to the formation of pi molecular orbital. Here, 2px orbitals overlap in a lateral fashion to produce two BMOs, two molecular orbitals. One is pi 2px BMO and other is pi star 2px ABMO. This is the pictorial representation of the lateral overlap between two 2px orbitals. Here there occur one BMO with the lower energy, that is pi 2px, and one ABMO with the higher energy, that is pi star 2px. Similarly, the lateral overlap between 2pz orbitals of the adjacent atoms leads to the formation of pi 2py bonding molecular orbital and pi star 2py antibonding molecular orbital. So, lateral overlap leads to the formation of pi molecular orbitals. Now we are discussing energy level diagrams of molecular orbitals. You know that whenever different kind of atomic orbitals overlap, different type of molecular orbitals are also produced. The obtained molecular orbitals may differ in their energy. It is possible to arrange various molecular orbitals in the increasing order of their energy, and this arrangement leads to a diagram that is called energy level diagram or molecular orbital diagram. We are entering into more details of energy level diagram or molecular orbital diagram. By the overlapping of atomic orbitals, first few atomic orbitals, 1s, 2s, 2px, 2py and 2pz, we will get 10 molecular orbitals. It is possible to arrange these 10 molecular orbitals in the increasing order of their energy to get an energy level diagram. Now a simple question is how 10 molecular orbitals are produced. By the overlapping between two 1s orbital, you will get 2 molecular orbitals, they are sigma 1s and sigma star 1s. By the overlapping of two 2s orbitals, you will get sigma 2s and sigma star 2s. By the overlapping of two 2pz orbitals, you will get sigma 2pz and sigma star 2pz. By the overlapping of two 2px orbitals, you will get pi 2px and pi star 2px. Similarly, the overlapping between two 2py orbitals leads to the formation of pi 2py and pi star 2py. So, on a sum, you will get 10 molecular orbitals, and these 10 molecular orbitals may differ in their energy, and it is possible to arrange these 10 molecular orbitals in the increasing order of their energy to get an energy level diagram, or this energy level diagram otherwise called the molecular orbital diagram. The obtained diagram is also known as the MO diagram or molecular orbital diagram. Now, we are discussing the molecular orbital diagram of homonuclear diatomic molecules. We know what is a homonuclear diatomic molecule. A diatomic molecule formed by the combination of two same atoms are called homonuclear diatomic molecules. Common examples H2, N2, O2, F2, etc. The MO diagram for homonuclear diatomic molecules with the regular energy order, with the common order is shown here. This give you an idea that there are some other MO diagrams with some alteration in the energy that we can discuss later in coming slides. Now we are focusing on the MO diagram of homonuclear diatomic molecules with regular energy order. This is the molecular orbital diagram. In a molecular orbital diagram, you have to note some important points. The left side and right side represents atomic orbital, and the middle portion represents molecular orbital. 1s and 1s combine together to produce sigma 1s and sigma star 1s. Sigma 1s is lower in energy, sigma star 1s is higher in energy compared with 1s. In a similar way, two 2s atomic orbitals combine together to produce sigma 2s with low energy and sigma star 2s with high energy. Similarly, here there are two p orbitals, 2px, 2py and 2pz. If you are taking 2pz orbital and Z is considered as the internuclear axis, the combination of 2pz orbital leads to low energy sigma 2pz and high energy sigma star 2pz. Lateral overlap leads to pi 2px and pi 2py. Also, their antibody molecular orbitals pi star 2px and pi star 2py. So, the 10 molecular orbitals are arranged in the diagram in the increasing order of their energy, and this diagram is MO diagram which follows regular energy order. So, from this diagram it is clear that sigma 1s is lower in energy than sigma star 1s, then followed by sigma 2s, then next energy level is sigma star 2s and so on. So, we represented 10 molecular orbitals in the increasing order of their energy, and in the MO diagram we also represent atomic orbitals. Now, the regular energy order based on the previous diagram for first 10 molecular orbitals are shown here. Sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, sigma 2pz. Then these two orbitals have the same energy, they are said to be doubly degenerate. So, pi 2px equal to pi 2py, followed by another doubly degenerate set, that is pi star 2px equal to pi star 2py, and the highest energy sigma star 2pz. This order is very important This you have to keep in your mind whenever you are representing MO configurations, and by using that MO configuration it is possible to calculate the bond order, which is a measure of the stability of the system. So, keep this order, that is sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, sigma 2p z, pi 2px equal to pi 2py, pi star 2px equal to pi star 2py, and sigma star 2p z. Now, we are discussing exceptional arrangement in MO diagram. It should be noted that in the case of second row elements, elements of the second period up to nitrogen, that is boron, carbon, nitrogen, in the diatomic case, the energy of the sigma 2pz orbital is slightly greater than pi 2px and pi 2py. This creates an exceptional MO diagram. So, the MO diagram for homonuclear diatomic molecules with exceptional energy order. What is the exceptional energy order? The energy of the sigma 2pz is slightly higher than pi 2px and pi 2py. If we are redrawing the MO diagram by including this exceptional arrangement, we will get a new molecular orbital diagram for exceptional case like this. Here sigma 1s is the least, followed by sigma star 1s, then sigma 2s, sigma star 2s. Now, you noticed the change, the position of the sigma 2p, that is sigma 2p z, sigma 2p z is slightly higher than pi 2px and pi 2py. Previously, it was at this position, and in the case of exceptional arrangement, energy of the sigma 2pz is slightly higher than pi 2px and pi 2py, and this is applicable to second row elements in the periodic table up to nitrogen. Now, hence we can rewrite the energy levels of such molecules or where there is exception. The exceptional energy arrangement can be represented like this: sigma 1s, then sigma star 1s, sigma 2s, sigma star 2s, then pi 2px equal to pi 2py, then sigma 2pz, pi star 2px equal to pi star 2py, and finally sigma star 2pz. So, this order is the exceptional arrangement or exceptional order which is applicable to second row elements in the periodic table up to nitrogen. Now, explanation for change in energy order. I just mentioned you that the energy of sigma 2p is slightly higher than pi 2px and pi 2py in the case of second row elements up to nitrogen. We are now focusing on why this happens or explanation for change in energy order. Due to sp orbital mixing, that is there may occur the s orbital mixing, s orbital may mix with the p orbital, that is taken as sp mixing, sp orbital mixing. The energy of the sigma 2p is higher than pi 2px and pi 2py for the elements with the atomic number less than or equal to 7, that is up to nitrogen. For elements with atomic number greater than 7, the energy levels shift, placing sigma 2pz lower than pi 2px and pi 2py orbital. So, the ultimate reason is considered as sp orbital mixing. Now, we are discussing molecular orbital configuration. We studied the formation of 10 molecular orbitals by the overlapping or linear combination of first 5 atomic orbitals, 1s, 2s, 2px, 2py and 2pz. We learned the energy order, regular order as well as exceptional order, and we are able to construct the molecular orbital diagram. Now, we are discussing how to fill electrons in the molecular orbital diagram to get molecular orbital configuration of a molecule. That is, we are dealing with molecular orbital configuration. Molecular orbital configuration describes the filling of electrons in molecular orbitals following Aufbau principle, Hund's rule and Pauli's exclusion principle. According to Aufbau principle, electrons are filling in various orbitals, either atomic orbital or molecular orbital, in the increasing order of their energy. Hund's rule states that pairing of electrons in degenerate orbitals happen only after all the available orbitals are singly occupied. Pauli's exclusion principle depicts the fact that the maximum number of electrons that can be accommodated in any orbital, either atomic or molecular orbital, is equal to 2, and these 2 electrons must have opposite spin. So, based on Aufbau principle, Hund's rule and Pauli's exclusion principle, it is possible to fill electrons in various molecular orbitals of a molecule to get the corresponding MO configuration. The total number of electrons in a homoatomic diatomic molecule is determined from the atomic number of the element. For example, in N2 molecule, the total number of electrons is equal to 7 plus 7, that is equal to 14. Because atomic number of nitrogen is 7, it may have 7 electrons. So, in nitrogen molecule, there are a total of 7 plus 4, that is equal to 14 electrons. Hydrogen molecule H2 has a total electron of 2, because the participating atoms hydrogen each has 1 electron, and hence for hydrogen molecule you can represent the MO configuration like this: sigma 1s 2. The total 2 electrons present in hydrogen molecule is accommodated in lowest energy bonding molecular orbital, that is sigma 1s. Therefore, the molecular orbital configuration of the hydrogen molecule is sigma 1s 2. You can take lithium molecule Li2, lithium with atomic number 3. So, in Li2 molecule there are a total of 6 electrons, and these 6 electrons can be arranged in molecular orbitals to get the MO configuration: sigma 1s 2, sigma star 1s 2, followed by sigma 2s 2. Now, you can take beryllium molecule as another example. Beryllium is having atomic number 4. So, in Be2 molecule there are a total of 4 plus 4, that is equal to 8 electrons, and these 8 electrons can be arranged in the molecular orbitals of Be2 as sigma 1s 2, sigma star 1s 2, sigma 2s 2, and sigma star 2s 2. Similarly, we can take the nitrogen molecule. As I mentioned, it is a system of 14 electrons. These 14 electrons can be arranged in molecular orbitals of nitrogen as sigma 1s 2, sigma star 1s 2, sigma 2s 2, sigma star 2s 2, pi 2p 2, pi 2p 2, sigma 2p z2. Nitrogen molecule shows some exceptional configuration. That is why the electronic configuration or MO configuration is like this. Oxygen molecule, there are a total of 16 electrons, and these 16 electrons can have this molecular orbital configuration: sigma 1s 2, sigma star 1s 2, sigma 2s 2, sigma star 2s 2, sigma 2p z2, pi 2p s2 equal to pi 2p y2, pi star 2p x1 equal to pi star 2p y1. You can see 2 odd electrons present in the last 2 orbitals. This is highly useful in predicting the paramagnetic behavior of oxygen molecule with respect to molecular orbital theory. Now, can you write the molecular orbital configuration of F2 molecule? Fluorine has a total of, F2 molecule has a total of 18 electrons. This is because each fluorine atom has 9 electrons since its atomic number is 9. So, we have to arrange 18 electrons for fluorine molecule. The 18 electrons can be arranged in the increasing order in various molecular orbitals like this: sigma 1s 2, sigma star 1s 2, sigma 2s 2, sigma star 2s 2, sigma 2p z2, pi 2p x2 equal to pi 2p y2, pi star 2p x2 equal to pi star 2p y2. You can see the arrangement of total 18 electrons in 9 molecular orbitals like this. Now, we are discussing another important parameter associated with the molecular orbital theory, that is nothing but bond order. After obtaining the molecular orbital configuration from MO diagram of molecules and ions, we can calculate the bond order of the system. The bond order is defined as half the difference between number of electrons in bonding orbitals and antibonding orbitals, or bond order equal to half of Nb minus Ni. Nb represents bonding electron and Na represents antibonding electrons. In the case of nitrogen, there are a total of 14 electrons with this MO configuration, and you can pick up bonding and antibonding electrons. Electrons present in starred orbitals are antibonding electrons, whereas electrons present in non-starred orbitals are bonding electrons. Now, on careful looking, we can arrive at the conclusion that the number of bonding electron is equal to 10 and the number of antibonding electrons equal to 4. You know there are a total of 14 electrons and these are antibonding electrons. These two are also antibonding electrons. So, number of antibonding electrons is equal to 4. Remaining electrons are bonding. So, a total of 10 bonding electrons and 4 antibonding electrons. Now, you can calculate a bond order like this, 10 minus 4 by 2, that is equal to 3. Now, we are having some examples for bond order calculation. F2 molecule is also here. In the case of F2 molecule, this is the electronic arrangement that we have already studied. On looking this configuration, you can arrive at the conclusion that there are a total of 10 bonding electrons and 8 antibonding electrons. Now, to take the difference and divide it by 2 to get the bond order. 10 minus 8 by 2 is equal to 1. So, bond order of fluorine molecule is equal to 1. Now, we can take beryllium molecule Be2. Here there is a total of 8 electrons and the electronic arrangement is sigma 1s2, sigma star 1s2, sigma 2s2 and sigma star 2s2. In this situation, number of bonding electrons is equal to 4 and number of antibonding electrons also 4, and bond order will be equal to 4 minus 4 divided by 2, that is equal to 0. Now, we are discussing significance of bond order. Bond order help us to understand the stability of the molecule. Higher the bond order, higher will be the stability. A zero value of bond order indicates that the molecule is highly unstable or not formed. Bond order gives the number of bond present between atoms. Higher the bond order, shorter will be the bond length. Bond energy directly proportional to bond order. These all are significant features of bond order. Now, we are discussing magnetic behavior of molecules. It is possible to predict magnetic behavior of molecules based on molecular orbital theory. Molecule exhibit either diamagnetic or paramagnetic behavior based on unpaired electrons present in molecular orbitals. By noticing the presence of unpaired electrons in molecular orbitals, you can predict the magnetism. Diamagnetic molecules having no unpaired electrons in the molecular orbital and are repelled by a magnetic field. Paramagnetic molecules having one or more unpaired electrons in the molecular orbitals and are attracted by a magnetic field. Examples of diatomic molecules include nitrogen. Here there are a total of 14 electrons. Looking onto the MO diagram, you cannot see any unpaired electron in molecular orbital. So, nitrogen molecule is diamagnetic. All electrons are here paired and hence no unpaired electrons, that leads to diamagnetism or diamagnetic behavior. Now, example for paramagnetic molecule, oxygen having a total of 16 electrons. This about the MO configuration of oxygen molecule. Looking onto this MO configuration, it is very well clear that you can see the presence of 2 unpaired electrons in the last 2 molecular orbitals. The presence of these unpaired electrons, the 2 unpaired electrons in pi star orbitals of oxygen molecule make it paramagnetic. That is, oxygen molecule is paramagnetic due to the presence of unpaired electrons in molecular orbitals. That all about the present module. Have a nice learning experience. Thank you.